Hello students, I am Divya Sri YV, working as Assistant Professor in the Department of ECE SJBIT. I am here to explain Module 1, that is Introduction and Methodology of Digital System Design using Verilog subject, which is an elective subject. These are the contents you are going to study in Module 1 in this class. The topics are Digital Systems and Embedded Systems, real world circuits, that is the abstractions what we made in the real world circuits. Few topics which will be covered is integrated circuits, logic levels and static load levels. So before starting with the topic, you need to understand what do you mean by the digital. Digital means whenever you are representing information, the information will have values. So if you are representing the values in digital system, we say it has two voltage levels, that is logic 0 and logic 1. Logic 0 refers to 0 volts, logic 1 refers to 1 volts. The main purpose of doing this or using the digital system is it has more reliability and accuracy of the system. So given with certain constraints like the cost, performance, power consumption, size, weight, etc., we are going to design a digital circuit system. Coming to the history of the digital circuits, initially we started with the mechanical system, maybe 100 or 200 years back. Then we switched over to electromechanical system, then analog electronic system. The main usage of these systems were in doing certain calculations which we found in our daily life, that is in the business systems or in any military application systems. But even though we have so many advantages in our daily life, we have a disadvantage as well. The disadvantages are sometimes we have an inaccuracy, sometimes we have a problem with the speed, and it has high maintenance. So in mid 20th centuries, the digital systems were initially built using the relays. Then the relays, I hope you all know how the relays works. It works like a switch. Blocking of current means the switch is off. If you are unblocking means open, means the current is flowing through it. So current is controlled by operating the relay, and this is how we used to operate the switches. So with the advent of this digital circuits, after relays we came across this vacuum tubes. All these digital televisions what we had earlier were all, and also the computers were all built using the vacuum tubes. Subsequently, in the few further years, transistors were developed, uh, which is a trademark or the benchmark in the digital industry. Then after the invention of the transistors, the ICs were developed. IC in the sense integrated circuit, where you can build multiple transistors on a single chip. So this was a major digital revolution in the industry. So as the manufacturing technology has developed, the number of transistors on the IC, it is doubling every 18 months according to the Moore's law. So now at this point we are in an era where a large systems are built using billions of transistors. So once we have built a different number of devices what we are using in our daily life, we need to relate that systems, how it is built, and how or what are the abstractions what we have made. Abstraction means we are concentrating on specific aspects. that are very much important to us, and we are hiding few aspects which are not of our interest. So that concept we call it as a abstraction. So in the digital era, where every electronic components are made up of the digital circuits or the ICs or the transistors, we need to represent the information in the discrete form, which is better understood by the digital systems. Say we are speaking, we speak to each other, we communicate with each other. So that audio signal, it is an analog signal, or if we can say an example of any pressure waveforms, it is a continuously varying analog signal. But when that has to be handled by the digital system, so that analog to digital conversion has to be made. You can see a figure of a waveform, right? So this figure represents a pressure waveform of a sound which is continuously varying over the time. You can see continuously varying over the time, and the discrete representation of the waveform, it is in the digital system. Okay, so you understood how a digital system, or how, what is the role of the digital system in our daily life, right? Each and every component what we make use, that is being used with the, or built with the help of the digital circuits. So hoping that Verilog HDL language is known to you, because this is the subject you have studied as a core subject in your 5th semester. Hoping that you all know the concepts. Let us take an example or a problem to make you understand how the real world industry situations can be converted to the Verilog code or to the coding. So there is a problem here. You have to develop a Verilog module that expresses the logical structure of the gate circuit as shown in the figure. We will show the figure. So there are a sensor signals and there are switch signals which are acting as the input, and the output is the buzzer signal. So this is a scenario. The scenario is, you have a factory. You have a factory that has 2 watts. 2 watts means 2 units, out of which only one is active at a time. The liquid in the vat, it is to be monitored at the right temperature, and the temperature should be between 25 to 30 degrees centigrade. Each vat has a temperature sensor to indicate whether the temperature is within the range, that is 25 degree and 30 degree. But the temperature sensors what we have is, it will sense above 25 and above 30 degree sensors. If it goes below, we don't have an option, so we have to build that concept in our code. So the watts have low level sensors also. Low level sensors are used to monitor the levels of the liquid in the watts. So there is a supervisor, he needs to be woken up by the buzzer when 3 conditions are not obeyed. That is, when the temperature is too high, that is above 30 degree, or when the temperature is too low, that is below 25 degree, or the level of the sensor is too low. So he has to select a watt which is in use. He has the option to select whether first watt or the second watt. So for this you have to build a circuit. So this is the circuit what we have for that industry situation. You have 2 watts here, you can observe here, watt 0 and watt 1. Each watt is having 3 sensors. These are the 3 sensors. I will explain watt 0. The same thing is applicable for watt 1 also. So you have 2 temperature sensor with sensors above 25 and above 30 degree. So above 30-degree sensor and above 25-degree sensors. But we need to sense if the temperature goes below 25, not above 25. So you have using a NOT gate here, because the sensor is giving the output when there is a temperature above 25 degree. We were interested in if the temperature goes below 25 degree. So it is a NOT gate operation. And the other sensor, it is the level sensor to monitor the level of the liquid in the vat. So whenever they are monitoring the temperature, suppose if both the conditions, that is if the temperature of the liquid, if it goes above 30 degree, or if the temperature of the liquid goes below 25 degree, we have used an OR gate here. So any one of the signal goes high means we have a signal at the output of the OR gate, first OR gate. And the other condition what we are monitoring here is the low level. So when the low level signal is made high, means the level of the sensor goes below the threshold value, you have one at this signal. So the output of the second OR gate will be 1. When any of these three conditions is not obeyed, you have a signal at the output which is fed to a multiplexer, 2:1 multiplexer. So similar to VAT 0, you have VAT 1, the operation remains same. The select line of the multiplexer is that person, that is the supervisor. He can select between the switches, select VAT 1 or select VAT 0. So based on the signal selected, the inputs of the multiplexer, it is passed on to the buzzer, which is the output, right? So this is how the circuit is modeled. So in order to write the Verilog code for this situation, we have named the variables like this. Okay. So using this naming convention, the code is written, the Verilog HDL code. Module VAT buzzer struct, that is the module name. The input and output ports are declared. Okay, these are all the input and output ports. The intermediate wires are declared as wires. 0 is used for VAT 0 and VAT 1 is indicated by 1 subscript. And we are writing the program in structural modeling style because since we have more number of gates, this modeling style will be suited better. So we are creating an instance for the gates. Which are all gates are present here is OR gate and NOT gate, and we have a multiplexer. So for the first VAT, that is VAT 0, we have created an instance and we have mapped the input and output gates appropriately. Similarly for VAT 1, and then the last part of the circuit is the multiplexer. So for that also we have created an instance and we have mapped the input and outputs appropriately according to the naming convention what we have done. And last, end module. This is how we can convert a real world situation into the Verilog HDL coding. The same program, this is a structural programming, the same program can be written using a conditional operator in this format. Okay, so take this as a small task to understand how do the conditional operator works, recall those concepts and understand. The next topic what we are going to discuss now is real world circuits. So in real world circuits, you have to concentrate on certain parameters and certain properties. Few are these things: integrated circuits, logic levels, static load levels, capacitive load and propagation delay, wire delay, sequential timings, power, area and packaging. Out of these 8 abstractions, we are concentrating on 3 in this class. The first one is the integrated circuits. As the name itself suggests, integrated circuit means multiple or many number of components is integrated on a single chip, that is a silicon chip. Flat piece crystalline silicon, that is a silicon chip. On top of it, we are going to integrate certain components. Uh, so, so how do these transistors are formed? Transistors are formed by depositing layers of semiconducting and insulating materials in certain shapes required, that is maybe rectangular, polygonal shapes. So, in order to connect these shapes of components, you are using certain wires, insulating wires, for establishing the connections. They are formed by depositing the materials. Usually, we make use of copper on the top of the transistors. In order to give the safety, we are using insulating layers in between. So, each chip will have a feature size which will be around tens of microns. Nowadays, we have ICs which is having 90 nanometer and 65 nanometer as the minimum feature size. So, depending on the feature size itself, we can say how many number of transistors can fit on the particular IC. So, the overall circuit complexity, it depends on the feature size. So, according to Moore's law, as I said, the number of transistors on an IC, it is doubling every 18 months. So, a rapid revolution is happening in the IC industries. Uh, Giving a brief knowledge about how this transistors and all works. So, here we have the first families of the digital IC circuit. We call that as a TTL logic, where it used bipolar junction transistors. So, after that came the CMOS industries, that is some complementary metal oxide semiconductors, which are based on the FETs. So, we know that P MOSFETs and N MOSFETs, how do they work and all. So, based on that, we have a figure here which depicts the CMOS circuits of an inverter which is built using a PMOS and a NMOS. So, I hope the operation of NMOS and PMOS is known to you. So, whenever you are connecting PMOS channel in the upward direction and NMOS in the lower, giving proper gates and the outputs, you will get an inverter. If you are changing the connections, that is some serial connections or parallel connections of NMOS and PMOS, you will get some other gates like AND gate, OR gate operation, XOR gate operation and all. We will study this in detail in the coming subject, VLSI design. So, here if your input, that is at the input side, if your voltage is low, then N transistor which is at the bottom, it is turned off, and the P MOSFET which is at the top is turned on. So, when the P MOSFET is turned on, you have a voltage which is pulled to the output, that is it is made high. Conversely, whenever you have a input voltage as high, then P MOSFET will be off and N MOSFET will be on. So, the output will be 0. This is how a transistor operates in a inverter circuit. Okay. So, the next part is the logic levels. So, the main thing what you have to understand about logic level is we will set one threshold. So, based on that threshold only we will say whether the input is 0 or whether it is 1. Okay. So, suppose the threshold voltage what we have set is 1.4 voltage. So, all the voltages which is less than 1.4 is treated as low, and the higher voltage is treated as logic 1 or high. So, if we keep this as a what you can say, benchmark or the threshold. So what happens here is, what is the practical problems we faces in the manufacturing industry? Few components are developed by few vendors and few other components will be developed by other vendors, so they may keep different thresholds. So when those two components are integrated with together, then they will have a confusion whether to take one vendor's threshold or to take the other ones. Okay, so see here, so 1.4 was the threshold which is set. Receiver may have 1.5 as the threshold, and the sender or the other part of the circuit may have 1.3 as the threshold, but the nominal one which one was set is 1.4. So there is a confusion which is basically because of that single threshold value which has been set. So in order to avoid this confusion, so what they thought is, instead of having a single threshold, we'll divide it into through two thresholds. Okay, so the two thresholds what they have set is 2 volts and 0.8 volts. Instead of setting 1.4, they have set 2 and 0.8. So according to these two thresholds, the voltages above 2 is set as 1 and the voltages below 0.8 is set as 0, and the intermediate levels is not at all interpreted as any logic values. Okay, so observe the figure here. So 2 is the threshold value and 1.8 is the other threshold value. So in spite of having two thresholds, again there is a problem. The problem here is with respect to the noise which gets added up. So this addition of noise will enter the illegal range, even though if the input is less than 2 volts, it might go above 2 volts, or if it is above 2 volts, because of noise that spikes, because of that spikes it may reach the lower voltage. So this is a problem what we face. So in order to overcome this, the final solution what we have done is, so we have divided the digital signals to drive the voltages lower than 0.4 as logic and 2.4 as high logic. Even though we have set as 2 and 0.8 in the previous figure, because of the noise which is added up along with the signal, there was, so the noise margin has been of 0.4 volts is been added up to both the levels. 2 volts which was the earlier threshold, now it is 2.4. 0.8 which was the earlier threshold, now it is 0.4, as you can see in the figure. So two threshold values along with the noise margins has been set. Okay, so what do VOL stands? VOH, VIL, VIH. So all these things are noted. The next topic is static load levels. This is the something like the second threshold assumptions what we have made. That second assumption is the current loads on the components are reasonable. Reasonable in the sense, this circuit, whatever the circuit you use, that can drive the output voltage. But in reality what happens, components will have certain internal resistance which will limit the current flow, right? So this idea is depicted in this figure. So we have switch 1 and switch 2. This have internal resistance R1 and R2. Okay, so the output can be pulled high when switch 1 is on, and it can be pulled low when switch 0 is closed or on. So one of the switches closed, the other will be open. So this is the scenario. So here, whenever switch 1 is closed, the current is sourced from the positive power supply to the output through certain load, that is resistance R1. And suppose if too much of current is flowing, okay, then R1 will protect. It will stop the current flow across the output. Okay, so it will make sure that the output voltage will fall below VOH. Similarly, the case with the switch 0. When switch 0 is closed and too much of current is sinking to from the load, then the current flow through this resistance R0 to the terminal, it has to be avoided. For that purpose, resistance R0 comes into picture. So it will make sure that the voltages will not go below VOL. Okay. So the amount of current which flows in each case, it depends on this output resistance. Okay. So the term static, it indicates that we are only considering the load when the signals are not changing. Remember this. Okay. And the current flow, it again depends on the term called fan out, that is how many number of inputs are connected to the output. Okay, so all these information will be mentioned by the manufacturer. Static load, it is the only factor that determines the maximum fan out. Okay, so when you have a circuit something like this, so how do this delay comes into picture? So you can look here. So you have a circuit where you have a resistor here and another resistor. In between you have a sub-circuit. For both the resistors we are applying a common clock, but they are connected through a wire. So when a wire comes into picture, definitely there will be a propagation delay which causes for a signal to flow from the input to output. So the delays which are introduced in this is TPDO, TPDC and TPD, TCO, TSU, setup time, clock to output time, propagation delay of the sub-circuit, propagation delay of the next stage. So like this we have certain propagation delay concepts, and all the summation, it should be less than the total cycle, clock cycle time. So that has been indicated in this diagram. So application of clock 1 and clock 2 is actually at the same time, but since you have a long wire which has a propagation delay, there is a certain amount of variations. Okay, so this is about the static load levels. Okay, I hope all the concepts are clear. If you have any doubts, you can revert back. The concepts which were discussed in today's class are: first we started with the digital system designing. What do you mean by a digital system, that we discussed, and then how do we the digital system, how the revolution got into place in case of digital systems, and we discussed a problem where industry situation is converted into the code. Then we understood integrated circuits, logic levels and static load levels topics. Okay, thank you.